Hi. Uh, Let me say a couple words about myself. I use Python for more than 15 years. I'm Python code developer, and I took a part in Async development, creating. I'm aiohttp maintainer. aiohttp is web library. This talk dedicated to this tool. And I and my friends provide dozens libraries under IO-lib's umbrella. It's Async compatible library. Today, my friend released first version of asynchronous Kafka client, by the way, so we are growing. At first, who used Python 3? Oh, very good. Because Async.io is Python 3 only library, and HTTP, of course, sure. Who use Python for development web sites with GI approach? I mean Django, Flask, whatever, except Tornado and Visit. Almost everybody. And who tried asynchronous frameworks? Raise hands, please, who use Async.io, aiohttp especially. Wow. So for others, it will maybe something new information. So why do we need asynchronous frameworks at all? Because we have Django, who don't want to use Django, who don't like it, can you use Tornado, Tornado, Flask can use perfect pyramid framework, but with VSGI approach, we have one crucial limitation. If our handler view some code responsible to sending request back should ask another resource, GitHub, on this page. Requests becomes very slow from computer perspective, and since with classic VSGI approach, we use one worker per thread, or it leads to CPU time waste. We don't use our resources in optimal manner. Our servers can handle about 1,000 of native auth threads, plus minus couple thousands. But with asynchronous approach, we can handle millions threads in parallel. This is a big win. Also, you know, there are web sockets and other interesting technologies which requires asynchronous communication style, not instant answer to requested site, but do something and send data when the data are ready. So HTTP is asynchronous-based web. When Guido and Rossum started develop Async.io and released Async.io library, it was very good designed tool, but Async.io is about sockets, not web sockets, but bare TCP sockets, pipes, subprocesses, and Async.io itself knows nothing about HTTP, about web protocols, about database. It's just about very low level communication channels. So we developed aiohttp. It has client API, server side. It supports persistent connections like keep alive, WebSockets, and so on. I'll tell you more. aiohttp all started as part of Async.io. Async.io named it Tulip those times because Guido was convinced that any successful asynchronous library should be named with starting with T letter. Tornado, Twisted, Tulip. But Tulip name was parked on PyP, so he renamed it into Async.io. Guido said web part was not ready for production, was not ready for Async.io release, so we dropped it from Async.io itself and released under aiohttp name. Now we have 21 release, about 3,000 commits, 100 contributors, and we feel also good enough. Client API. Async.io, aiohttp, sorry, consists from two overlapped parts. One part is client API. It's small and relatively easy. Other biggest part is server side code, and overlapping part is about HTTP protocol handling and other low-level stuffs. I'll start from client API. Requests. I believe everybody know request library, very famous and very good done. In request, we'll have just request get method, which fetch page from GitHub in this example, and we get a response object back. A response has status code, has headers, has text, response body. This is example for requests. For aiohttp, we have almost the same. You see, again, aiohttp get instead of requests get. Again, status, headers, text, but there are differences. And differences are, it's not a regular function, but async function, async def function. And before every waiting call to aiohttp, we should put await keyword. I'll tell you about it a bit more. How it changes our code? What async def and await means? It's very easy. Function, async def function, called coroutine. Just remember this name. If you should call coroutine function, you must push await keyword before function call. And if your function has await inside, it should be coroutine itself. So it's like a coroutine poison. If part of your code has coroutines, very quickly almost all of your code becomes coroutine also. Coroutine is very close to regular Python function, but it different in one point. Coroutine can be suspended on yield points. One Rossum called this point yield points. Now it awaits. On await statement, on await keyword, coroutine can be suspended if right side is not ready. So in this example, we want to sleep for 1 second. And our function, func, will be suspended until 1 second applies. And after that, coroutine will wake up and continue its execution. Yield point mostly is not about timeouts or sleeping, but waiting for data from network, waiting for some I/O. Under coroutine concept, there's a lot of code and not trivial things, but for casual usage, it's very, very simple. It looks like regular function with awaits inside. Next step. For effective HTTP processing, we not must, but better to support keep alives. Keep alives are very important because if client and server both support it, connection between client and server established only once, not on for every HTTP request, but once per session. So on using only one socket, we can download HTML page itself and JavaScript, pictures, CSS, whatever. In requests, we should use session object and call get method from session. For HTTP, almost the same. We also have a session, but you see we use async with syntax. Async with works almost very similar to classic with statement, but both enter and exit code can use await inside. Why I use this syntax as an example? Just to make sure that response will be closed after fetching HTML page. It's required for releasing resources. Timeouts. When we develop client code, we should care about timeouts because it's real internet, and real internet can hang for minutes, even for hours, without sending any error code back, without notifying about connection closing, but just some part of hardware and software between our code and server may hang for some reason. Lose internet packets and so on. So it's very easy to just push with statement, with timeout, and write code as usual. WebSocket. It's a simple example how to use WebSockets. Instead of writing put, get, whatever, we call as connect. This call establish WebSocket connection, upgrade HTTP transport to WebSocket, and after this call, we can receive messages from WebSocket server, send back, do what we want. I finished client side. Do you have questions? No. Okay. Yep. I use Async for and Async with. They internally use a little bit modified protocol. Usual for does what it does. It calls Thunder method iter and get iterator back and call next again Thunder method next underscore next underscore on iterator and until receive stop iterator exception. Async for calls a iter with a prefix. It's coroutine and return back asynchronous iterator with a next method. A iter and a next may have a wait inside. So I may wait for next message. Sleep on it. You can think about like switching context, allowing to other part of program to work. That's it.
Okay, I'd like to know what is the actual proxy support for the client part? Is the same as requests? Is as complete? Is it as complete as requests one?
We don't support SSL proxies. We support unsecured proxies and proxies to which you can connect unsecurely and upgrade to SSL. Okay. And pull request for SSL through SSL proxy is welcome for sure, but I don't know how this protocol works, and I don't need it for my works.
Okay. Anyway, kudos for it. It seems very elegant, that particular solution, because when you're used to use async frameworks in Python 2, for this is my case, it's a yield spaghetti, you know?
Yeah.
Okay, and this one seems very elegant, so it's one of the reasons I'm looking for going to Python 3. So kudos.
Thank you. Let's go to server part. At first, Django. I believe everybody know Django, at least can read Django code. So we have index view, accepting request parameter, and return response with some body. We should register our index in URLs py under patterns and create some settings py and start Django application. When we developed server side of aiohttp, we pursued this target. We wanted to have almost the same code with minimal changes, minimal required changes to make very well-known synchronous code. It's not only about Django. Flask looks very similar also. we want just to make it asynchronous. What we get in the result? We have, again, index view. We prefer to call it handler, but it's view, actually. But it's not def, but async def. It means inside we can do any asynchronous stuffs, execute asynchronous code. It accepts requests also, returns response with body. To run this view, you should create application, fill a route table, and run application. That's it. It's very, very close to Django code. How to do it in Tornado? In Tornado, it's aiohttp competitor. Frankly speaking, it's much more popular than aiohttp for now, but I always compare aiohttp with Tornado. In Tornado, we have a request handler with methods like get, post, head, whatever. User should override this method, use self-write to send answer, create Tornado application, start it, and again, not very big difference between aiohttp and Tornado. But crucial part is in aiohttp, our code is just function. We can write class-based views if we need. aiohttp supported. In Tornado, we should derive from some predefined class and modify it. Sending static body back is perfect, but we need some communications with databases, with Redis, Mongo, whatever. This is example for Postgres library. For now, under IO-libs umbrella, we have client libraries for MySQL, for Postgres, for Redis for sure. This autumn, Jesse Davis released Async.io compatible motor driver for MongoDB. I told about Kafka client. So we have many supported databases and key value storages. So for Postgres, this is initialization code, create metadata, SQL alchemy metadata, describe, define tables, indexes, whatever, and create engine, not SQL alchemy engine, but our own engine. The problem is SQL alchemy is really perfect library. I love it. But SQL alchemy built for synchronous style. It has no places to push await inside. To make alchemy asynchronous, you should just rewrite it. So we cannot use SQL alchemy ORM layer, but can borrow alchemy's query languages. I show it on next slide. So it's not 100% compatible replacement, but some way to work with databases. And don't fight with boring string concatenation for building a SQL query. So we created engine, pushed it into application. Application has dictionary especially for global things. I hate singletons and suggest always use some context. Context for push database connection is application. We register cleanup code on application closing, on server stopping. We can just drop it, but better to make some graceful shutdown. So last close DB function is about is for shutdown procedure. And more interesting slide is request performance. Our handler acquires connection from DB engine, execute some code. You see insert. Well, it's actual the same code you can write in with SQL alchemy, and iterate on select result. Return response back. Very easy. But it's not object relation mapper. It's just a bit easy way for constructing SQL strings than just writing select from and concatenating parameters. We support server-side WebSockets, for sure. Code is very close to client one. The only difference is instead of establishing connection to server, we upgrade client's request to WebSocket protocol. That's it. I described you basic usage level. With this knowledge, you can write some site. It's not very hard, not much harder than using Django or Flask, but battery amount is limited, you know. Next slides will be dedicated about two more complex techniques. Every web framework, big web framework, has middlewares. We have two. Middleware is code which will be executed before request processing and after processing. It looks like two hooks. You see onion, and every middleware is like onion layer with web handler in very core. Why do you need it? First example. There is a library called aiohttp session. Obviously, it's for server session support. So you see in this library, we get session from request. Session is key value storage. You can test values in session. You can read it. You can store new values under some keys. And you see, we just return response. We don't save session. How it works? You have a middleware which will save modified session automatically after returning response from web handler. Not very exciting. Another example, I love it. It's the battle bar. This debug toolbar was ported from Pyramid. Pyramid steal it from a Flask. Django has own debug toolbar, so every framework should have it. It's a side application. You can see requests, middlewares, internal variables, tracebacks in case of error, as shown on this slide. You can click on these buttons to open console and communicate with your server. All this work done by middleware. It's complex middleware for sure, but it's a very good demonstration why do you need some additional extra layers over your web handler. Oppa, sorry. How it works inside. It's a long story, but I'll try to be short. Excuse me. Couple things for understanding. In heart of Async based code sits event loop. Event loop runs every Async program. And inside event loop, there is a selector. It's true for Unix-based systems. On Windows, situation a bit different as usual. Selector works with sockets, with file objects. It's not only sockets, but also it may be pipes, files, files itself on Linux are blocking, so you will get no benefits from handling files via Async. Selector has three main methods: register, socket for read or write events, unregister, and select, waiting with timeout. Selectors Async has selectors for select, for poll, for epoll, for QQ, for all modern Unix implementations. Linux use epoll, for example. And event loop selector or wrapper has reader, add reader, remove reader, add writer, remove writer, and functions for timeouts like call soon, call later. Just for calling callback with parameters immediately or after some delay. And how it works internally. It's infinite loop which forever asks selector for some events with specified timeout. Process a reading event by reading data from sockets, writing event by pushing data to sockets back, and processing all timers which are ready. You should know, when you write data into sockets, it goes to internal operation system buffer, not into network, and definitely not into other peer. The same for reading. So socket communicates with buffers, and when network data becomes available, a reading event raises on, and selector can inform our code. Our code can process this data from socket. The same for writing. For timeouts, let's see. We are here now. We have 2 expired timeout events, and one of them was cancelled. It happens. We should process expired timeouts. We have 2 pending timeout events, and we will wait for this time. And our system will wait for this with this delay for either network activity, some data socket will be available, or timeout expiring. This means we should execute that timeout code. Very easy. Why I told about it? Just to reflect the fact, most of time, if our system is not under high load, it just sleeps. Sleeps, waiting for timeouts, waiting for network events. It's not run forever trying to boil universe. Common mistake. Now you know. If you have no very high load, systems is sleeping. That's it. And what I want to recommend you when you develop Async IO code. I found writing tests is very easy. When you start a client, test client, and test its server in the same process, in the same event loop. Just look on aiohttp test suite itself. It's very convenient debug if your communicating parts not split into different processes or event threads. But for deploying, you can cut your big system into parts, run admin side on one server, user visible part on other, some long running processes on third, and so on. Python Async IO debug. It's very interesting thing. This snippet shows the problem. We created future. Future is, I believe everybody knows what future is. At least it's from a JavaScript world. It's the same. Object with delayed value. After creation, it's empty. We push exception into future and delete it immediately. Forget an exception. It's programming error. Async IO will display text like this. Future exception never retried. It's a bug. But you don't know what future produced, what future was deleted without retrieving exception. To solve it, run your code with Python Async IO debug environment set it up, and you will see traceback with file names and line numbers. Why don't run it always? Just because it's slow. It's good only for development, not for production configuration. Another advice, Async IO has implicit loop. always in any place can get loop by async IO get event loop call. But I suggest passing loop everywhere. It's just good practice. It saves time. It saves, I don't know, hours of debugging. Because when two different loops start to interfere, you don't know, just don't know why your timeout don't expire. Why some event don't happen? Because you probably use different loop. Last thing is testing. Testing async IO code is a little bit different than classic testing, because with unit test, standard unit test library, test function should be just function. It cannot be coroutine. So we create test function, regular function, and run coroutine inside it, waiting for finishing nested coroutine. Very easy. And also very good practice to create new loop before every test and shut it down after test execution. If you don't do it, you can add very funny effect, like you created a test, test finished, but some pending activity still scheduled. And it may be active on execute next test execution or after next test. To avoid it, just prepare a clean environment for every test. Last slide. Performance. I don't care about performance right now because main slowdowns are not inside aiohttp but async IO. It's written in pure Python with pure Python, so it's not very fast. It's just as fast as Tornado. I think it's good numbers. And my friend works on faster event loop. It uses libuv internally and not with Python but Cython, Cythonized. I don't know. It at least 1.5 times faster than standard. So that's it. Questions?
Are there any questions? No questions? All right. Thank you, Andrew, for this talk.